Alright, welcome back to the final and last video of the past year paper series. This time we're doing paper 4 instead of paper 5, and we're going to discuss 9701 paper 42 of the Feb-March 2023 series. So this one is going to be a past year paper walkthrough where we discuss the answers to the questions thoroughly. Okay, so by the way, I'm not going to be using the transitions because I don't know how to return to the previous slide if I'm applying it, so it's easier for me to do it this way. Okay, question 1a. The most common zinc mineral contains zinc sulfide, zinc 2 sulfide. Complete the electrons in the boxes diagram in figure 1.1 to show the electronic configuration of a zinc 2 ion. Alright, so again, zinc 2 ion essentially refers to zinc 2 plus, and if we take a look at the periodic table, it falls under the D block section. So there is a shortcut as it's right in the middle, so that would be D block. And then you can count the order from 1 to 10, and it falls under 10, so it's 3D10. And we know for 4s 4s comes before 3D, so you're removing 2 electrons, right? And that 2 electrons are removed from the 4s orbital, so it becomes 4s0 instead of 4s2 and becomes 3D10. So yeah, you have 10 electrons in the 3D orbital. Alright, question II. Complete figure 1.2 to show the Born-Haber diagram for the ionic solid zinc sulfide. Include state symbols of relevant species. Alright, so we know that in room temperature, both zinc and sulfur is initially in solid state. So yeah, that's why they would be in solid state. And for atomization, again, you're turning it into gaseous atoms. So firstly, your zinc will turn into gaseous atom, and your sulfur will then follow right after. After that, we have IE, or ionization energy. We have already learned this in AS, where you basically removed an electron to form an ion. So yeah, you have 2 ionization energies, so you're removing 2 electrons, and yeah, that sums up. Alright, next question. Describe the trend in the first electron affinity of group 16 elements from S to Te. Alright, explain your answer. Okay, so this one, basically for the whole of physical chemistry, it's very concept heavy. You have to remember, and if you don't, that's very unfortunate, but you can try to use some of your AS knowledge. But basically, down the group, the electron affinity becomes less exothermic. Why? Because the atomic radius increases and the nuclear charge attraction decreases. So yeah, down the group, atomic radius increases and nuclear charge attraction decreases. That's why your electron affinity becomes less exothermic. IV. Explain why the lattice energy of zinc oxide is more exothermic than that of zinc sulfide. Okay, so for your oxide ion, it has a smaller ionic radius compared to your sulfide ions, so there is going to be a higher forces of attraction between your zinc and your oxide, so it becomes more exothermic. That will be your answer. Alright, again, let us discuss further for your electron affinity. Alright, the full definition, it's basically the enthalpy change when 1 mole of electron is added to 1 mole of gaseous atom. Alright, so usually your first electron affinity is going to be exothermic, so yeah. And whenever I put an arrow, it refers to less exothermic, by the way. just to clarify that. And the factors affecting includes nuclear charge, so when it decreases it becomes less exothermic, and when the distance increases it becomes less exothermic as well. So for, again, lattice energy, right, it is always exothermic no matter what, no matter if it's like the lattice energy of this or that, it is always going to be exothermic, always going to be negative. And the factors which affects it is actually quite similar. First, we have your ion size, so the smaller it is, the higher the force of attraction, so the more exothermic it is. But in this case, right, it has the same charge. Usually the charge also has like an effect. If the charge increases, then your lattice energy also becomes more exothermic, but this time around they're the same charge, so it doesn't really matter. For B, zinc metal can be obtained in a two-step process as shown. So we have step 1, zinc sulfide plus oxygen, you're getting zinc oxide and sulfur dioxide. Step 2, you're getting zinc, the liquid form of zinc, and carbon monoxide from zinc oxide and carbon. The reactions are carried out at 800 degrees Celsius. Predict the sign of the entropy change of the reaction in step 1. Alright, so what exactly is entropy? Entropy is basically a measure of the disorderliness of the system. So if it's like gas, it's more disordered. If it's liquid, it's more disordered than solid, but less disordered than gas. So the answer would be negative for step 1 because there are more gaseous reactants than products. Alright, as you can see, the ratio of gaseous product is only 4 and the ratio of gaseous reactant is 5, so it becomes negative. You have more gaseous reactants than products. Alright, use the data in table 1.1 to calculate the entropy change of the reaction shown in step 2. So we have the entropy change for all of them, and by the way, you have to memorize this formula. So the entropy change of a system is going to be the entropy change of a product minus the entropy change of a reactant. Again, remember it's minus bracket on whatever the entropy change of the reactant is. If it's negative, then you're going to obviously plus it. So in this case, it's positive, so you have the entropy change of your products, so 50.8 plus 197.7, that would be your products, your CO and your zinc in liquid form, minus 43.7 plus 5.7. The plus 5.7 is inside the bracket, by the way, so you're going to minus it as well. And the final value is plus 199.1 joule per Kelvin per mole. Alright, next question. An equation for the direct reduction of zinc sulfide by carbon is shown. Okay, the reaction is not feasible at 800 degrees Celsius, so you expect it to be positive for the Gibbs free energy. Alright, so by the way, make sure to always read the question properly. So in this case, they're trying to trick us as they are using kilojoule for one of them, which is your enthalpy chain, and using joule, only joule, not kilojoule, for your entropy. Alright, so, okay, what is the formula for your Gibbs free energy? It is delta H minus T delta S, which is your entropy. So yeah, there's a lot of formulas involved that you have to remember, but if you actually do remember, it's quite easy. So yeah, your Gibbs free would be 733 minus the temperature, which is in Kelvin, so make sure to convert it from degrees Celsius to Kelvin by adding 273, or you can minus it if it's in the negative. And yeah, you times it by your entropy, and make sure to again convert it to kilojoule. And the end value is plus 499.086. Alright, okay. Question C. Zinc nitrate undergoes thermal decomposition when heated. The reaction is similar to thermal decomposition of group 2 nitrates. This one, yeah, you can flash back to AS, we already memorized it, right? The thermal decomposition of nitrates, you will obtain an oxide, and you obtain nitrogen dioxide as well as half of oxygen molecule. So yeah, make sure to actually balance the equation as well. It is very important that you don't miss that out. Alright, so for II, the radii of some group 2 cations and zinc 2 plus are shown in table 1.2. So we can see the different radius. So you can see the trend generally like increases going down the group except for zinc. Alright, okay. So state and explain the trend in thermal stability of the group 2 nitrates down the group. Alright, the group 2 nitrates will likely increase in their thermal stability down the group because their cation radius decreases. Causing less polarization. The cation radius is not supposed to be decreasing, but it's supposed to be increasing. So we'll fix that mistake. It is actually supposed to be increasing. Alright. So causing less polarization of anions and less weakening of NO bond. So yeah, down the group, higher radius, less polarization of anions, less likely to be decomposed, and less weakening of bonds. So make sure to remember this one is supposed to be increasing, not decreasing. For question II, use table 1.2 to suggest which group 2 nitrates are less thermally stable than zinc nitrate. So, okay, we can take a look at the radius, which one has a smaller radius. That would be your magnesium cation. So yeah, your magnesium nitrate would be the one that is less thermally stable. Again, just find the one with a smaller radius than your zinc 2 plus. Alright, next question. Question 2. Hypophosphorus acid is an inorganic acid. The conjugate base for hypophosphorus acid is H2PO2-. So this one is fairly easy, right? Acid just add H+, so yeah, the charges is balanced. It is balanced and it becomes H3PO2. That would be your hypophosphorus acid. Okay, so question B. H2PO2- is a strong reducing agent. It can be used to reduce metal cations without the need for electrolysis. So you're given the equation, alright? So, okay, gaining of electrons, so reduction is the forward, oxidation is the backward. In an experiment, an alkaline HPO32- H2PO2- half cell is constructed with H2PO2- with the concentration of 0.05 moles. So you're changing it from the standard concentration of 1. Alright. So all other ions are at their standard concentration, and predict how the value of E of this half cell differs from its electronegative value. Alright, explain your answer. Okay, so your E value is more positive as the concentration of H2PO2 becomes lower, right? And this causes the equilibrium to shift to the right hand side, causing more reduction to occur. So as you can see, once you decrease, if this one is decreased in concentration, alright, then this one will try to move it to the left hand side because you would try, sorry, if this one has decrease in concentration, it will move to the right hand side because it will try to balance it, because again it's in equilibrium. All right, and this causes more forward reaction to occur, so more reduction, and yeah, that's why your E value sort of increases, becomes more positive. All right, by the way, you can answer it in terms of equation, like there's an equation where you can find out the E value, but recent past year paper actually requires answer in terms of equilibria, so it's probably safer that we do that instead. All right, okay. So the Cr3 plus Cr half cell has a standard electrode potential of negative 0.74 volt. An electrochemical cell consists of an alkaline HPO32- and H2PO2- half cell and a Cr3 plus Cr half cell. Calculate the standard electrode potential of the cell. Alright, okay, so the standard electrode potential would be the potential for reduction minus the potential for oxidation. This is, again, a formula, you have to memorize it. So yeah, 1.57 minus 0.74, alright? That's why you get 0.83, and this one is in positive value, so plus 0.83 volt. Sorry, just have to remove the volt here so it is not duplicate. Alright. Okay. Complete the diagram in figure 2.1 to show how the standard electrode potential of the Cr3 plus Cr half cell can be measured relative to the standard hydrogen electrode. Identify the chemicals, conditions, and relevant pieces of apparatus. Alright, so for this question, again, the standard conditions would be your 1.0 mole per decimeter cubic of your H plus, because we're using standard hydrogen electrode, right? You would expect your hydrogen gas to be in 1 atm, and you would use platinum. You can also use graphite or carbon as long as they are inert and they can conduct electricity. So yeah, we're using platinum here because it's the best, and it's submerged in a solution of 1.0 mole per decimeter cubic of H plus. Alright, and the other one, it is connected with your Cr electrode. Alright, and your Cr electrode is submerged in the standard solution of 1.0 mole per decimeter cubic of Cr3 plus. Alright, and also with this, you would usually be required to create a salt bridge, which are usually, yeah, you would also need to add a salt bridge and your voltmeter. Don't forget that, because we're doing standard hydrogen electrode. Okay, question IV. Label figure 2.1 to show which is the positive electrode and the direction of the electron flow in the external circuit. Now, which one is the positive electrode? Your platinum here, this is the, why isn't it? Alright, this is your positive electrode, right? And your chromium here, this is the negative electrode. So what is the flow of electron? So we know that electron is negative, right? So it flows like anti-clockwise from your negative electrode to your positive electrode. So yeah, it's in this direction. Alright, question V. H2PO2 minus reduces Ni2 plus. So if it reduces something, then it itself gets oxidized. So yeah, it reduces Ni2 plus to Ni in alkaline condition. Use equation 1 to construct the ionic equation for this reaction. Alright, okay, so this one is fairly simple. You just have to use the backward reaction. Alright, and you're just going to add your Ni2 plus, which initially it was Ni2 plus, and then it gets reduced to your Ni. Alright, next question. H2PO2 minus reacts with OH minus. Table 1 shows a result of series of experiments used to investigate the rate of this reaction. Okay, so this one is usually your, order, first order, second order. Alright. Okay, so the volume of H2 was measured under room conditions. Use the molar volume of gas Vm and the data from experiment 1 to calculate the rate of change in mole per decimeter cubic per second. So, okay, the formula here would be change in concentration over time. So this one would be 6.4 over 24,000. So you times it by 1 over 60, that would be 4.44 times 10 to the power of negative 6. Alright. Okay. The rate is found to be KH2PO2 minus, aqueous and OH minus. This one is part by 2 because that one would be your second order. Yeah, for your OH minus. And alright, show the data in table 2.1 is consistent with the rate equation. Again, we can see here that the concentration of H2PO2 minus increases by 2 times for experiment 1 and 2. And the volume of H2 produced also doubles, by the way. Here, it doubles. So this gives indication that this one is first order. Alright. And when your H2PO2 for 2 to 3, it increases by 1.5, and your OH actually decreases by 0.5. So you would expect it to be 0.375 if one of them is second order, because the volume of H2 decreases by 0.375. It indicates that you times it by 1.5 and then times it by 0.5 square again, and the relationship is in squares, so this indicates that this one is second order. So again, this confirms your H2PO2 minus is in first order and your OH minus is in second order. State the units of the rate constant K for the reaction. Again, the unit is fairly simple. Usually it's mole per decimeter cube per second, but this time around we got mole squared per decimeter power of negative 6 and per second. Okay, question IV. The experiment is repeated using a large excess of OH minus. Under these conditions, the rate of the equation is this one. And your K value, K1 is 8.25 times 10 to the power of negative 5. Alright, the formula for half-life is actually ln2 over your K1, but usually your ln2, yeah, you can round it up to 0.693, so 0.693 over K1, and that is 0.693 over 8.25 times 10 to the power of negative 5. And the answer would be 8,400 seconds. Alright, question V. Describe how an increase in temperature affects the value of the rate constant. Again, this one is very straightforward. K1 increases with temperature because, yeah, And also, an increase in temperature increases the rate of reaction. That's why K1 is directly proportional with your temperature. Alright, question D. Students suggest that the reaction between H2PO2 minus and OH minus might happen more quickly in the presence of a heterogeneous catalyst. Describe the mode of action of a heterogeneous catalyst. So again, your reactant will diffuse to the surface of the catalyst and becomes physically absorbed, not absorbed, but absorbed to the surface by the weak forces, and this becomes chemically absorbed to the surface by stronger bonds. And the absorption will then causes bond weakening between atoms and reactants. So that is basically the mode of action for heterogeneous catalysts. Always mention about the weak forces. It is physically absorbed on the surface by weak forces and then chemically absorbed onto the surface by stronger bonds. So they are two different stuff, chemically and physically absorbed. And yeah, also mention that the absorption causes the bond weakening between atoms and reactants. Alright, for next question, question 3. By the way, we're still dealing with inorganic. Yep, here transition element exactly at inorganic. So the previous question was mainly organic, sorry, not organic. The previous question was mainly physical, and yeah, we've just reached inorganic. Okay, so what is transition element? Right, vanadium is a transition element in period 4 of the periodic table. So define what is transition element. I guess this one has to be memorized. Yeah, a lot of the inorganic section actually requires to be memorized. Alright, so for 3A, what is transition element? It is a d-block element which forms one or more stable ions with incompletely filled d subshell. That is the standard answer. Mention it is d-block element which forms one or more stable ions with incompletely filled d subshell. Alright, question B. Vanadium shows typical chemical properties of transition elements, including variable oxidation states. So there's usually 4 if we add variable oxidation states, but if we remove that one, we have 3. So first, they can form complex ions, they can form colored compounds, they can also act as a catalyst. So question II. Explain why the transition elements have variable oxidation state. Again, this is because their S and D subshell are very close in energy level. They tend to overlap because they're so close. So for question C, VO2 plus can be reduced to V2 plus by C2O42 minus in acidic conditions. So this one is getting reduced, as you can see. And in a titration, 25 centimeter cubes of 0.03 mole per decimeter cube of VO2 plus is added to 10 centimeter cubes of dilute sulfuric acid. Alright, so with this information we can count the amount of mole present, which is your volume times your concentration. Make sure to convert it into decimeter cube, by the way. Alright, a solution of 0.04 mole per decimeter cube of C2O42 minus is then added from a burette until the endpoint is reached. That titration is repeated and concordant results are obtained. So again, we can apply the same stuff, right? Just times it half times the different values, so you get the mean, alright? The mean of the volume of C2O4 minus added, C2O42 minus added, sorry, and you convert it to your decimeter cube, times it by the concentration, and you have the amount of mole. And yeah, you just do the ratio, 7.5 times 10 to the power of negative 4, and 1.13 times the 10 of negative 3, that would be 1 to 1.5. Alright, An excess of C2O42 minus reacts with VO2 plus to form a mixture of two octahedral complex ions. Each complex ion contains a V2 plus cation and 3 C2O42 minus ion. Complete the diagram to show the three-dimensional shape of one of the complex ions. Include the charge of the complex ion. So the charge would be 4 minus. Alright, yeah, and this one would be the diagram for your complex ion. This one. And yeah, as you can see, it's bonded to a central cation. And yeah, you can see 3 C2O42 minus ions. And the overall charge is 4 minus, because why you have 3 times minus 2, which is negative 6, and plus 2, that would be negative 4. So yeah, that's why the charges is negative 4. Alright, V2 plus aqueous can be oxidized by H2O2 aqueous. The table 3.2 gives some relevant data, so you have the value. Alright, and the half equation. Identify the vanadium species that forms when excess H2O2 reacts with V2 plus. Alright, so okay, so what you're trying to get here is the answer that contains the most positive E value. Alright, so that would be your VO2 plus. Okay, so yeah, VO2 plus, the one here. Alright, question II. Concentrated acidified H2O2 can react with V2 plus to form red VO2 3 plus ions. VO2 3 plus contains vanadium combined with the peroxide anion. Deduce the oxidation state. Alright, so it's fairly simple. Negative 2, and you add it with the oxidation state of vanadium, you're supposed to get plus 3. So what? Plus 5 to balance it. Yeah, so your V is plus 5 because you already have 2 minus and you're trying to get plus 3, so you add plus 5, that would be the oxidation state. Alright, now we have reached organic chemistry. So yeah, that was quite a lot. We still have like nearly half of the paper left, so we'll move forward. Alright, ethylamine and phenylamine are primary amines. Alright, sorry. So these two compounds are synthesized by different methods. Several methods can be used to form ethylamine. Ethylamine forms when ethanamide, is reduced by LiAlH4. Write an equation for this reaction and use H to represent one atom of hydrogen from the reducing agent. Again, this is your final product and this is your reactant. Right, as you can see, there's no O in your final product, so the O has to go somewhere, and that one goes to your water, H2O. Alright, so CH3, CO, and H2 plus H is going to be CH3, CH2, and H2 plus H2O. Make sure to balance it with 4 hydrogen. Alright, ethylamine is a product of the reaction of bromoethane with ammonia. So ammonia loves nucleus. And the name of the mechanism of this reaction, and state the conditions used. Again, write ammonia, nucleophile, nucleophilic substitution, so that'll be the mechanism. And the conditions, again, ethanol, heat under pressure. You have to memorize this, because if you don't, then yeah, you're not getting the mark. This one is also very content heavy, by the way. The reaction in AII also forms secondary and tertiary amines. So your secondary amines would be CH3, CH2, and H, and your tertiary amine would be CH3, CH2, N. Alright, suggest the identity of the secondary or tertiary amine formed by the reaction in AII. So for this, you can actually pick either. I picked your secondary amines instead of the tertiary, but yeah, you can pick any. Alright, question B. Ethylamine is a weak base. So this one is a classic question. They ask you to order the relative basicity. There's also another one for, I believe, the strength of your CCl bond, something along the lines of that. Those two usually comes out a lot. So always remember that phenylamine is the least basic, ammonia is right in the middle, and your ethylamine is the most basic. So phenylamine is the least basic because it has overlapping of p orbitals on n with pi bonding system in your benzene ring. So what happens because of this? Because of this, it causes the lone pair to actually be delocalized into the benzene ring's electron withdrawing nature. So yeah. But for your ethylamine, it's a different story. Ethylamine's ethyl group, however, is electron donating, and this causes a release of moving electrons towards the N atom and increasing the N's electron density. So because of this higher electron density, the basicity is increased. So your ethylamine has the largest basicity, and the basicity is basically ordered based on the ability to donate its lone pair. Alright, for question C, pure phenylamine C6H5NH2 can be prepared from benzene in 2 steps. Draw the structure of the intermediate compound and suggest the reagents and conditions for each step. So yeah, this one is a 2-step reaction. So your initial reagent would be your benzene. You have your benzene and you want to obtain pure phenylamine. So you have to use concentrated HNO3 and H2SO4 at 50 degrees Celsius so you can form your nitrobenzene. Alright, so yeah, to form your nitrobenzene, concentrated HNO3 and H2SO4 is added at 50 degrees Celsius. And once you obtain your nitrobenzene, you want to obtain your phenylamine. So what do? You reflux it, right? Reflux with tin or SN with concentrated HCl and followed by NaOH. This part is like mentioned in the syllabus, so don't forget to mention that. Alright, it is reduced with tin with concentrated HCl and then followed by NaOH, which is your alkali. Next question. Question 4. Question 4D. Figure 4.2 shows some reaction of the phenylamine. So yeah, that one is your phenylamine, and you react it with excess bromine. So if it is again excess bromine, all position is activated. So 2, 4, 6 likely to be activated. So the structure of W, as you can see, 2, 4, 6. All are activated. State the reagents used in reaction to. Which one is reaction to? Alright, so you're forming benzene diazonium chloride from your phenylamine. So you would be using HNO2, and usually that one is formed from NaNO2 and dilute HCl. And this is usually conducted at below 10 degrees. This one is not as, but usually at less than 10 degrees to prevent decomposition to nitrogen gas. Alright, benzene diazonium chloride C6H5N2Cl and X react together in reaction 4 to form Y, an azo compound. Name X the organic product of reaction 3. So, alright. Organic product would be phenol, because as you can see here, right, this is phenol. So yeah, X is likely to be phenol. And then state the necessary conditions for reaction 4 to occur. Again, alright, this one is fairly simple. NaOH has to be done in the presence of an alkali. And V suggests a use for Y. So Y is your azo compound, and all azo compound can be used as dyes. Alright, so question E. Methylamine CH3NH2 is another primary amine. CH3NH2 can act as a monodentate ligand. So what is monodentate ligand? It is a species that forms one dative covalent bond, or you can say coordinate bond, bonded to a central metal atom using one lone pair of electrons. Alright, so those are the keywords. So one dative covalent bond or coordinate bond. Usually I use dative covalent instead of coordinate just to not get mixed up with like maths and stuff. And yeah, it is always bonded to a central metal atom. You can also say it's bonded to a central metal ion using one lone pair of electrons. Again, for monodentate is single. There's usually bidentate and other types of ligand. If it's bidentate, then it's double. Alright, so Cu2 plus reacts with CH3NH2 to form CuCH3NH22 and H2O4. Alright, so you have 2, 4, that's 6, that is in octahedral. So yeah, that is the shape. Draw the 3D diagram to show the two geometrical isomers of CuCH3NH2, 2 of H2O4, 2 plus. Alright, so usually for this, it's cis and trans. How do we know which one is cis? How do we know which one is trans? Alright. So for your trans, your methylamine here, right? They're like directly opposites of each other. So it's like 180 degrees away. Alright, and also make sure that the bond are pointed to the donor atom. So that's why it's like OH2 instead of H2O, because the donor is your O. And again, for your cis, alright, as you can see, your methylamine, they are like in the same side. So yeah, it's like 90 degrees. It's not directly across each other. That's how you identify which one is cis, which one is trans. Alright, question III. State the coordination number of copper in CuCH3 and H22 H2O4 2 plus. So again, you just look at the number of bonds bonded to central metal atom. How many do we have? 1, 2, 3, 4, 5, 6. Coordination number is 6. Okay, question F. CD2 plus ions form tetrahedral complexes with CH3 and H2, OH minus, and Cl minus, as shown in equilibrium 1, 2, and 3. Alright, give the unit of, oh my god. Alright, I have accidentally erased it. So it is mole, sorry, we'll just rewrite it. The value again, alright, this one is not negative. Okay, that would be the value, the K stability value. Alright. So, okay, I'm back. Here, give the units of K stability for equilibrium 1. So you can see equilibrium 1. Alright. This one only 1. The ratio, this one is 4. So, yeah, 4 and 5. So, yeah, 4 by 5, you cross it out. So, yeah, it's mole power of -4 and decimeter power of 12. So it's product over reactant. Alright, so 1 over 5. Okay, write an expression for K stability for equilibrium 3. So again, it's product over reactant. So this one is your product for equilibrium 3, and these are your reactant. Alright, so the molar ratio in front will be powered. So yeah, that's why it's powered by 4. Alright, next question. Question triple I. A solution of Cl- is added to Cd2 plus and allowed to reach equilibrium. The equilibrium concentrations are given. Use expression in Fi to calculate the concentration of CdCl4 2-. Again, this one is product over reactant, that is your K stability, and you already have it, just plug it in, and what you have to do is essentially rearrange so that this one could go to this side, and yeah, 6.3 times 10 to the power of 2 times the value of the concentration. This one is powered by 4, by the way. This is powered by 4. And yeah, you get the concentration of CdCl4 2-, which is 7.28 times 10 to the power of negative 4. When CH3NH2 is added to Cd2 plus, a mixture of CdCH3 and H24 2 plus and CdOH4 2- forms. Suggest how CdOH4 2- is formed. Again, your CH3NH2 will act as a base, and then it accepts your proton from Cd. CdH2O6 2 plus. That is how your CdOH4 2- is formed. It accepts the proton. Alright, Cd2 plus exists as a complex ion. Identify the most and the least stable of the complexes by placing one tick. Alright, again, your least stable is CdH2O6 2 plus, and your most stable is CdOH4 2-. Why is that? Because CdOH4 2- has the highest K stability value, K stat value. Yeah, again, the higher the K stat value, the more stable it is. And your CdH2O6 2 plus has the lowest K stat value. Alright, for question 5a, tolobutyrol. Alright, this question, I've seen it more than once, so not sure if it's a repeated question or not, but do take note. Alright, explain the shape of the benzene and describe it. Alright, in your answer, include the bond angle between carbon atoms. Again, this one fairly simple. This is all theory, 120 degrees, trigonal planar, and the hybridization is sp2, so yeah, this one doesn't look very nice. I will explain that later. The orbital overlaps to form your sigma and pi bond. So for your sigma, it's the overlapping of sp2. Kind of looks like a fish, like this, and they like overlap like straight on. Yeah, that's what they're referring to. Like, yeah, end to end. And for your pi bonding, it is due to the sideways overlap of the p orbitals. So yeah, it's sideways. It's different type of overlap. Okay, so how do you approach this question? 3 marks. We can approach it by first mentioning the shape. So the benzene shape is trigonal planar with a 120 degrees bond angle between the carbon atoms that are sp2 hybridized. And the sp2 hybridized orbitals, they will overlap head-on or end-to-end to give the sigma bond, and the p orbital overlaps sideways to give the pi bond. There are also delocalized electrons within the pi bonding system. That would be enough for more than 3 marks actually. That's how many marks in total? That would be 5 marks. So yeah, just have to mention 3. Alright, in the synthesis of tolobutyrol, the first step involves the formation of chlorobenzene. Benzene reacts with Cl2 in the presence of AlCl3 catalyst. So again, you're trying to generate your Cl plus electrophile here. So yeah, Cl2 plus AlCl3 becomes Cl plus and ACl4-. It's not ACl, AlCl4-. Alright, question II. Complete the mechanism in figure 5.3 for the reaction of benzene with the electrophile generated in Bi. Include all the relevant curly arrows and charges again. So first we have the electrons towards your electrophiles. Alright, Cl+, and your intermediate would be your CH, and it's towards the positive, and yeah, pair of electrons from your CH will move to the benzene ring, and yeah, this is your end product. 3 marks. This is actually very generous. You only have to remember how to do the mechanism and you obtain 3 marks. Alright, for question CI. The second step of the synthesis involves the reaction of chlorobenzene with ClCOCH2Cl, also in the presence of an AlCl3 catalyst, forming compound Q. So what exactly is compound Q? Compound Q is your acylation product. So alright, once you add it with ClCOCH2Cl, there's 2 possible electrophiles, right? You either get your acylation product or your alkylation product. So for your alkylation, basically pretend that this one is gone. So where is it? Pretend this one is gone. That would be your acylation product. And for your alkylation product, pretend that the other Cl is gone, like the one is here. So you have here acylation, alkylation. Alright. Now, although they might look similar, there's a slight difference. As you can see, this one is bonded to O. This one is not. It's bonded to a C atom. Alright. Okay. Name the mechanism of reaction in step 2. This one is electrophilic substitution. Again, question II. Draw the structure of an isomer of Q that forms as an organic byproduct of the reaction in step 2. Alright, so for this one would be your alkylation products. So yeah, this is the end product. So just imagine your Cl here, alright, and your this section is like gone, so it's bonded straight on directly. So sorry, yeah, it's this one is for your alkylation product, not acylation, sorry. For the reactants used in step 2 contains acyl chloride, alkyl chloride, and aryl chloride. State and explain the relative ease of hydrolysis of acyl chlorides, alkyl chlorides, and aryl chlorides. So again, your acyl is easiest to hydrolyze because, as you can see, they're bonded to 2 different electronegative atoms. And for your alkyl chloride, right, you have your CCl minus bond, but for your aryl, like your Cl minus is directly bonded to the benzene system itself, so your lone pair of electrons can get delocalized. So yeah, that's why it's very difficult to hydrolyze. Again, the answer is because the carbon in CCl in your acyl chloride is more electron deficient, as it is attached to 2 electronegative atoms. However, the CCl minus bond in aryl chloride, they form a partial double bond character, as the lone pair from Cl delocalize in the benzene ring, so the CCl bond is stronger. Alright, we have reached nearly the end. Just 3 more slides. Okay, tolubuterol is produced from Q. Alright, okay, so we can see the difference, O into OH and the removal of Cl, and you substitute your amine. Okay, alright, suggest the reagents and the conditions. So obviously you want to reduce your double bond O into OH, right? So yeah, you can do that. Actually, you can do that in step 3 or step 4. The order doesn't matter. Either order is fine, but in this case, I'm writing it in step 4. So my step 3 would be the substitution. So yeah, you place it in ethanol, heat under pressure with CH3, 3CnH2, because that is the amine used. Alright, draw structure of Z. Okay, this is the structure of Z. So, yeah, right before it is getting reduced. Alright, question E. The synthesis produces two enantiomers of 2-lobutyrol. Define enantiomers. So enantiomers are essentially stereoisomers. They're a pair of stereoisomers that are non-superimposable in mirror image of each other. So I'll rewrite it. Impossible mirror image of each other. Non-superimpossible, not superimpossible. So yeah. So just one disadvantage of producing two enantiomers in this synthesis. So obviously if you produce two, right, it might reduce the biological activity because less concentration, and you might actually require separation to get the pure active optical isomer. And the method of producing a single enantiomer is by using a chiral catalyst. So always have that remembered. Okay, so for question Fi, predict the number of peaks that will be seen in carbon-13 NMR. So yeah, this depends on the equivalence carbon. So this one is all the same, but this one, because it's bonded to Cl, it's not the same anymore, so they're no longer equivalents. So there's like 6 different carbons. Alright, so the total number of peaks again, these are all the same. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the total is 10. Alright, the proton NMR spectrum of 2-lobutyrol dissolved in D2O shows peak in 4 different types of proton environment. Alright, the peak for CH2 and environment is a doublet. So, okay. What happens when you dissolve it in deuterium D2O, heavy water? So your peak will disappear for like OH and NH. Why is that? Because of proton exchange. Alright, so give the details for each of the 3 other peaks in the proton NMR. So chemical shift, environment of the proton, splitting pattern, number of H atom responsible. Alright, so as you can see, there will be a singlet with 9H at 0.9 to 1.7 ppm. So that would be your alkane. Good environment of protons is alkane. Which one is that? This one is your singlet. Alright, and there will be a triplet with 1H at 3.2 to 4 ppm, and its environment of proton is alkyl oh my god. Alright, alkyl next to electronegative atom. So which one is that? That one would be this. Alright. So again, for the next one, there is going to be a multiplet with 4H at 6 until 9 ppm with the environment being attached to aromatic ring. So which one is that? This one is here. So yeah, that would be your multiplet with 4H. So that gives you 3 marks. Always refer to the table for reference of the chemical range, by the way. Alright, question 13. So a student is using a thin layer chromatography TLC to analyze a mixture containing different metal cations. The student repeats the experiment using different solvents. Alright, suggest the compound that could be used as a stationary phase. Again, we just learned this, Al2O3, also known as your alumina. Alright, suggest the identity of cation that causes the spot at M. So we can find the RF value by using the distance traveled by your M over the distance traveled by the solvent. So 2/5, 0.4, that directly aligns with CD2+. Alright, the student repeats the experiment using butane 1-ol as solvent, which is again less polar. The metal cations do not travel as far up in the TLC plate in this experiment suggests why the metal cations do not move as far up. Alright, it is less polar, then it means the ion dipole forces would be weaker. Alright, weaker with butane 1-ol, and the metal cations become less soluble in your butane 1-ol. Alright, the students praise the TLC plate with KSCN, so it's K plus SCN minus. The color of the spot changes, again exchange of ligand, so H2O is exchanged with SCN minus. This is fairly standard. Alright, we have reached nearly the end. It is for question D. Just 2 more. Right, in a third experiment, the pH of the mixture of metal ions is kept constant using a buffer solution. The student prepares the buffer solution by mixing 20 centimeter cubes of 0.15 mole of KOH and 50 centimeter cubes of 0.1 mole of C8H5O4K, which is a weak carboxylic acid with a pKa of 5.4. Alright, complete the equation again. Right, this is your acid form, you add your KOH, and this is your salt form. So yeah, you just have to plug it in into the equation form. So you have C8H5O4K plus KOH becomes C8H4O4K2 plus H2O. Alright, calculate the pH of the buffer solution. Show all of your workings. Alright, so this one is actually not that difficult, but it's very time consuming and a lengthy process. So what you want to do first is find the initial mole of KOH and C8H5O4K. You do this by timesing the concentration with the volume. Make sure it's in decimeter cubes, so you have these two values. Alright, and because your KOH here is your limiting, the mole of salt is going to be the same as your mole for KOH. So 3 times 10 to the power of negative 3. And the mole of acid would be 5 minus 3 times 10 to the power of negative 3. So it becomes 2 times 10 to the power of negative 3. Alright, so what is your pKa? pKa is 5.4, and we know we can get the anti-log for this. So yeah, 10 to the power of negative 5.4. So this would be your Ka. So what is the formula for Ka? So Ka is your, again, H plus times by salt concentration over acid concentration. So you're trying to find the H plus, right? So again, you can just plug in the value divided by the total volume, which is 0.07. And yeah, you can actually cross it out and you obtain the value of H plus, which is 2.65 times 10 to the power of negative 6, and you just basically log the value and you get 5.58. That would be your pH. Alright, this also sums up the end of the question. Thank you for watching and thank you for listening. Overall, I personally find the question to be very heavy, very long. Matter of fact, it's supposed to be done in 2 hours, 100 marks in total. So yeah, not a surprise here.